We're going to start this video with a nice video of Rainy. Rainy is the dog that never causes any problems. Behind Rainy is Hattie. I wish I could say the same. Anyway, I love both of these dogs very much, and that's not relevant to you so much. But what is relevant to you is that today we're going to be talking about population models for two competing species. So we're going to start by introducing, let's say we're going to have two populations, X and Y, Rainies and Hatties. No, maybe not. And I'm going to tell you something about these populations. I'm going to tell you that the rate of change of that first population is going to be double the current population times 1 minus that population over 2. Let's stop right there. Pause. What is this telling us? This is logistic growth, right? This is our growth rate. This is our carrying capacity. And then we can make this model a little bit more interesting by subtracting an X times a Y. This is saying that, okay, these species are competing for resources. So the more X and Y there are, right, they're going to scale multiplicatively to cause a decline in the population of the X's, right? That's a negative term. It's going to talk about what causes population X to decline. Here's a positive term. That's going to cause population X to increase. Well, I guess this is only positive if we're below the carrying capacity, right? Because if we're above the carrying capacity, then this will also become negative. I'm going to say we have another population as well, dy dt. And that population grows according to this model. And again, it has it starts off with logistic growth. It has a faster growth rate. It has a bigger carrying capacity. Okay, the second population is looking pretty strong, right? But then we're also going to subtract 2 times X and Y. So we can see that, okay, this species is punished more for, like, maybe they require more resources or something like that, or they're more impacted by the presence of that X population, right? They have a bigger negative factor here. And again, we're only going to look at anything in the first quadrant because we're looking at populations. Okay, so we're going to do a few things with this model and get some practice talking about everything that we've done in chapter 2 so far. First step was interpreting the model, right? Recognizing logistic growth, recognizing that these are, like the species competing for the same resources. This is what's going to cause a decline in these populations, right? Being able to analyze all of these terms is really, really useful. So next up, spoilers, sorry. Next up, we're going to look at equilibria. So where are the equilibrium points? Well, remember, equilibrium points are going to be the vector values that cause both rates of change to be 0. So we're going to say, well, when is 2x times 1 minus x over 2 minus x times y equal to 0? And when is 3y times 1 minus y over 3 minus 2xy equal to 0? And okay, we have to solve that. I love algebra, love systems of equations. Hopefully you remember how to solve them. There's a couple of ways. I don't think there's really any good way of eliminating variables like here. We could maybe do some sort of substitution. We could maybe do some level of factoring. I actually have no idea what this solution is going to look like. Let's clean up. Let's factor the first one a little bit and see what happens. I didn't actually look this far ahead. If we factor out an x, what do we get? We're left with 2 minus x. Here, right? If you factor out an x, this is just 2. This is minus x. And then minus y equal to 0. And the other one, we can factor out a y and get something very similar, right? We're going to get 3 minus y minus 2x equals 0. So, of course, we can immediately see that if x and y are both 0, we have an equilibrium point. All right, so let's just make a note of that. 0, 0 is an equilibrium point. All right. Well, what else could make things equal to 0? Notice that as soon as we have things factored, you know something factored equals 0 when either piece equals 0, right? So if both of these are 0, that's one equilibrium point. If these are 0, we have another equilibrium point. If these are 0, we have another equilibrium point. And if these are both 0, we have another equilibrium point, right? So all the ways that we can get equilibria. So when you do that, right, you're going to get the following. If x is 0, we see, okay, when is this piece? It's going to be y is 3. When y is 0, we're going to need this piece, which is going to be 2. And finally, what happens if we have both of these at the same time? And the answer is, I don't know. We're going to have to solve that system of equations. And I believe if we subtract these systems, then what we're going to get is -1, the y's cancel, plus x equals 0. X is equal to 1. And if x is equal to 1, what is y equal to? 2 minus 1 is 1. Y also has to be 1. So using our algebra skills, which I didn't know whether I even had, apparently I do still have algebra skills, which is great. Hopefully you do as well. Here are our equilibrium points. And again, we could say what are our equilibrium functions, right? Our equilibrium functions would be the constant functions 0, 0, right? There's other ones as well, 0, 3, right? However we want to write these. We have multiple equilibrium solutions, and they are just the constant functions equal to the equilibrium points. And again, the notation the book uses is a little ambiguous whether you're talking about points or vectors. Technically, these are all vectors. Okay, so that's the first thing that we can do for this. Next, let's look at the direction field, and I'm going to remind you, and by remind you, I mean I'm going to tell you that the same thing we use for slope fields can also be used to plot direction fields. Just when you go up here to plot your slope field, just click over here to system. All right. So let's do something with x's and y's. And we're going to say we have 2x times 1 minus x over 2 minus x times y. It doesn't like, I think you need multiplication here. I don't remember. And then over here, we're going to have 3 times y times 1 minus y over 3 minus 2 times x times y. And we are going to have something that I may or may not have typed in incorrectly. 2x times 1 minus x over 2 minus x times y. 3y times 1 minus y over 3 minus 2 times x times y. And then what we're going to do is make sure these are right. Okay, I think these are just too big. I have a backup plan if this doesn't work. Yeah, these are just too big. Great. All right, now we can see something a little bit more interesting as we zoom in a little bit. Wonderful. All right, so we can see now our direction field. And what I'm going to do is I'm actually going to copy this direction field down so that we can write on it. Okay, so if I do that real quick, let's snip, snip. Copy the direction field down. Let's draw on it. I want to draw some solutions. All right, so remember what we said for solutions, right? We just kind of, any starting value we want, we just follow the arrows. All right, so if we start over here, for example, we're going to follow the arrows and go to here. All right. Wait, hold on. Where exactly are we going? Let's cheat a little bit. And by cheat, I mean let's use our resources. Let's plot the equilibrium points first. What are our equilibrium points? 0, 0 and 0, 3. Oh, interesting. 2, 0 and 1, 1. Oh, 2, crap. 2 is over here a little bit behind my camera. And then 1, 1 is right here. And so you can see that no matter where you start, maybe you start there and you go there. Maybe you start here and you kind of follow these. Right, you can see some interesting behavior. Over here, it kind of looks like we get pushed away from it a little bit maybe. It's kind of hard to see a little bit on some of these. Right, like look at where we're going in a lot of these. This one's a little weird because remember, solutions aren't really going to cross. Solutions aren't really going to cross as long as we have uniqueness, and we're going to have uniqueness as long as certain nice things happen. And by remember, I mean I'm going to remember because I wrote that in my notes, but actually I wrote that to tell you right now. Just like in first order differential equations, we have a uniqueness theorem. We'll also have a uniqueness theorem for these systems of differential equations, and it's going to work pretty similar. We won't have solutions crossing, provided we have uniqueness, and we'll have uniqueness in most nice situations. That's covered in 2.5, which again, we're not really going to talk about. So just know that most nice systems have uniqueness, and a lot of the models that we're going to talk about are also nice systems. So we could plot a lot of these ourselves, and this is sort of what we're going to get. And I think, if I remember right, no, I don't. But I can also show you a nicer phase portrait here from the book. You can get something that looks very similar to what we drew. Right, so these solutions are either, right, most of these, this is actually, I think, maybe an unstable point. I'm not quite sure because they didn't actually include arrows on theirs. But yeah, many of these are approaching one of these side equilibria. 2, 0 or 0, 3. Again, if you're looking at the directions, honestly, I like mine better. If you look at the directions, usually one of the populations is dying out. Okay. Usually we're approaching this one or this one that's behind my camera. And if there's two competing species, yeah, it's bad news for one of them, according to this model. All right. But if we start over here, they'll kind of live in perfect balance. And again, this is just a guess. These are just us following curves. We don't actually necessarily know what's going to happen until we get a little bit more into chapters 2 and 3. Again, we can also use we can also use numerical techniques, just like we could with slope fields. We can click on here, and they will use, I believe, Euler's method to plot some solutions. And you can see that for all of these different initial conditions, we have different things happening. And yeah, we can definitely see, right, this is kind of some kind of unstable equilibrium. Things are not actually approaching 1, 1. They'll get close to it, but they'll bounce off. And you can see that really all of these are approaching either one species dying off over here or the other species dying off behind me. All right. But yeah, you can see how these vectors follow no matter where we start. And we can get some ideas of the behavior here. Isn't that cool? And again, this is something you can play with yourself. Just go to the Slope Fields website, hit the system button, and type your own system. You can either click or type your initial conditions manually over here. Right? And then again, you could also go to negative time if you wanted. But pretty cool, right? I think that's most of what I wanted to talk about here. Last thing I want to comment on is, again, we could also use numerical techniques to talk about time. Direction fields have nothing to do with time. Direction fields are not vector fields. Vector fields at least kind of show you how fast these are. Direction fields have all the vectors the same length. So we have no idea about how fast any of this is happening. Whereas if we use numerical techniques to plot these solutions, we can see some of this, right? Notice we have two initial conditions over here. This first initial condition, x, is this dark one, but they're both pretty close to each other, right? The initial condition for x and y are both pretty close to each other, and we can see that they both grow to about the same amount, but then y starts taking over. And as y starts taking over, x is going away. Whereas if x already starts with a lead, well, x is just going to take over pretty quickly, and y is going to be kind of going away here. So you can see some behaviors for different initial conditions, right? You can see y is approaching that equilibrium for y, and x is dying off, whereas x, if x wins, right, x is approaching that equilibrium of 2, which again, remember, those were the carrying capacities. Remember, the carrying capacity for x, if there was no y, the carrying capacity for x was 2. The carrying capacity for y was 3. So again, we saw that both in the equilibrium points, y of 3 was an equilibrium point, x of 2 was an equilibrium point, and we saw that graphically with the direction field as well. We can also see it with different solution curves for different initial conditions. Again, y is asymptoting to a y value of 3 if y wins out, and if x wins out, x is asymptoting to an x value of 2. Okay, and again, I kind of cut it off here, but over here, this is the t axis. All right. Whew, that's a lot. So finally, just a reminder that in chapters 2 and chapter 3, we are pretty much exclusively going to be talking about autonomous differential equations. Autonomous differential equations, because if you see here, right, x and y are both functions of time. So time is in here. But there is no time variable explicit. There's no independent variable on the right-hand side explicitly. It's only implicitly in these functions x and y. And again, here x and y do depend on t. X and y are functions of t. And in chapter 2 and chapter 3, we're only going to look at autonomous systems. And then in chapter 4, we talk about non-autonomous systems. Whew, that was kind of a lot. Putting it all together, looking at this population model. Again, you should know how to interpret and create systems of differential equations. You should know how to find equilibria. You should know how to use a computer to plot a direction field and kind of interpret that direction field by plotting some sample solutions for different initial conditions. If this is our initial condition of x is about 0.6 and y is about 3.5, you should know what's going to happen by following these arrows. All right. And again, this is an approximation, just like when we were doing slope fields, just an approximation. We don't know for sure what's happening. We're just going to try to follow the arrows. And we know the arrows really aren't going to cross much. The curves aren't really going to cross much. The solutions aren't going to cross much because of uniqueness. And we'll have uniqueness in certain nice enough situations. Most of this class will be nice enough. You don't need to know how to find these curves. You do need to know how to interpret these curves and how to relate these curves with this vector field, or direction field rather. Okay, so that part is important. That's pretty much it for 2.2. Hopefully the geometry of systems is interesting to you. I think there's a lot of cool things, lots of fun graphs. They all relate to each other. It can be a lot, but again, seeing all the connections is why differential equations is so cool. So it's exciting to me. Hopefully it's exciting to you. Have a great rest of your day. And until next time, remember the next 2 sections, we focus on analytic techniques to certain nice enough systems of differential equations. See ya.